All right, the final two examples are very, very simple. They look really complicated because they have two radicals. And by the way, because we're spending an extra day with this work, the next lesson we're not doing. You can take a look at the next lesson if you like, and I might discuss it a bit with you tomorrow. But the next lesson in your handout is very complicated, and it's optional, but I usually like to include it. But we're not going to for time reasons this year. This is really simple. In fact, you might make an argument that it's simpler to work with this than it is to work with any of the other examples we've done. Even though there's two radicals, we can arrange it so we have a radical on each side, and in one swipe of the pencil, we can get rid of both radicals. If I square both sides of this equation, which is what we're allowed to do, this becomes 3h minus 4. This becomes 5 minus 6h. Well, that's a grade whatever equation. It's a junior high, maybe upper elementary school math problem. I would move the 6h to the other side where it joins forces with the 3h to get 9h. I would add 4 to both sides, so that 4 is going to add to the 5 to get 9. 9h equals 9 means when you divide both sides by 9, you get h equals 1. I mean, 20 seconds to solve this. If you're writing really fast, 10 seconds. We still have to check that, so I'm not going to, well, I guess I'll do it on paper. The left-hand side is 3 times x. We got x equals 1 minus 4. The right-hand side under the radical sign is 5 minus 6 times 1. So what do we end up with here? We end up with 3 minus 4 under here, which is the square root of negative 1. And here we have the square root of negative 1. Well, this is interesting, because those are the same thing, aren't they? But this is not a solution, because the square root of negative 1 doesn't exist. It's like saying that. You just have two things that don't exist. I know that a unicorn and a witch are different things, but if they're non-existent, how can we even say they're different? The square root of negative 1 doesn't exist. When you check for an extraneous root, what you want is a true mathematical statement. And the square root of negative 1 is not a truth in high school math. In post-secondary math, it has a meaning, but we would never go there. So there's no solution. There's a way I can show you that there's no solution here, and I think this is worthwhile, even though we only talk about this method of solving these in Math 30. Let's use our graphing calculator and enter for y1, let's enter the square root of 3x minus 4. The reason, so we're going to solve this graphically, and the reason why we don't officially do this in Math 20 is you don't understand what these graphs look like. But I can show you what this graph looks like. It's like half of a parabola laying on its side. We've learned in various places in grade 10 and 11 so far that if you plot this as y1 and this as y2, then wherever they intersect, that will be the x-coordinate of that point would be the solution. So I'm going to also graph the square root of 5 minus 6h, or well, 6x. It will also be a parabola laying on its side, but it turns out it's pointing the other way, and these two things never are identical. There's no place where they intersect, so there's no solution. Okay. Just in preparation for next year, we got 1 for a solution. 1 is not a solution, so we call it extraneous. You will never see an extraneous root on the graph because It doesn't exist. That's the meaning of extraneous. Let's try one more example here. We have about 4 minutes left and we can do this. This might look more complicated than the previous one, but it's really the same idea. We just need to do a slight rearrangement of the terms by adding that negative radical to the other side, where it becomes positive. Then we can square both sides. That's all. And I realized that yesterday I could have slipped these two examples into the final part of our day, but I wanted to give you some extra time for practice. When I square the left-hand side, I get 15k plus 4. When I square the right-hand side, I get 11 minus 6k. So now it's just a matter of us rearranging and solving for k, double-checking to see if k, the value we get, actually works. So if I add 6k to both sides, I get 15k plus 6k, which is, better check my math this morning because my brain is still firing up, I guess, 21k. Okay, and I subtract 4 from both sides and get 7. Be very, very careful here. This is a slippery kind of equation, not because it's complicated mathematically, but I see a lot of students, good students sometimes, look at that and go, oh, k equals 3. Because they see 21, they see 7, they're used to getting a whole number. We have to divide both sides by 21, so what you get is k equals 1/3. And now what we can do is double check that. 7 divided by 21 is 1/3. We can check that against the original equation. And you might say, and technically you would be correct, can't we check it here? But I want to impress on you the importance of always checking it against the original equation. Always the original. So we had root 15k plus 4 minus root 11 minus 6k, I believe. Yep. So, and this is supposedly equal to 0, and we got 1/3. Did I write that down correctly? Okay. So we have 15 times 1/3, and then plus 4, minus, that's under a radical, minus 11, root 11 minus 6 times 1/3. 15 times 1/3 is 5. 5 plus 4 is 9. Root 9 is 3. Minus 6 times 1/3 is 2. 11 minus 2 is 9. The square root of 9 is 3. 3 minus 3 is 0. So we can go back over here and summarize our work. So what we're going to be doing this afternoon is basically, first of all, continuing to work with any of these assigned problems dealing with square roots. Some of them were not assigned yesterday. But not this one and this one. I'll talk this afternoon about those two and why we can't do them. They have to do with the lesson that's tomorrow, was planned for tomorrow, but I'm deleting from this year's course. I will also have a list of problems for you dealing with extra practice with multiplying, dividing, rationalizing to prepare you for the quiz. So when the bell rings, have a wonderful rest of the day, and we will talk to you later.